So next, we're going to explore an interchange of variable technique when we're dealing with non-rectangular regions. Recall, we already talked about in the last section with Fubini's theorem the fact that we could interchange our order of integration, meaning that we could do the x's first or the y's first, and it didn't matter. The problem with Fubini's theorem is that it only applies when you're talking about rectangular regions. Rectangular regions are nice because you always have constant values on all of your bounds. Whereas here we have an example of a function where we don't have constant values, that we have some region of integration. And so this example, we're looking at a double integral where our x values are going from 0 to 1, our y values are going from y equals x to y equals 1. We're trying to integrate the function sine of y squared dy dx. But notice when we try to actually compute this integration, it's not going to work. Why is it not going to work? It turns out for this specific example, I have this composition function. I could integrate the sine of y, but as soon as I add y squared, it's a composition of functions, and I need to use a u substitution. But there's no u substitution available that would allow for this integration. Actually, if I were to evaluate this algebraically, you'd have to do a Taylor polynomial, and then you would have to integrate term by term. That's something that we aren't going to do. Fortunately, we have the ability to interchange our order of integration, and that's going to help out a lot. We can't just naively interchange our x's and y's, however. For interchanging variables, we have to go back to what the region is actually describing. So that's the stuff that I'm going to describe here. So let's take a look at this region of integration. So I'm looking in the xy axis, and I know that the bounds on x go from 0 to x equals 1. And I know, so this is where x equals 1. I know the bounds on y go from y equal to x, that's just the line with slope 1, up until y equals 1. And I know that all of these points intersect at this point because where x equals 1 and y equals 1 is the same place where y equals x. So it means that I have all these crazy lines. What is the region of integration? I know that my x values are going from 0 to 1, so I'm somehow bounded in here. My y values are bounded from below by this line and from above by the line y equals 1. So in this case, my region is the triangle up here. Notice that the way that this is written, my triangle is described as a type 1 region, meaning that it's my y values that are functions of x's. In order to interchange the order of integration, I'm going to have to flip from a type 1 region to a type 2 region. I'll write that down. To change order of integration, you need to flip from type 1 to type 2. Or if it was originally a type 2, we would have to flip it to type 1. That you have to flip your type of region in order to flip your order of integration, because we're going to have to describe our bounds in the reverse order. So let's go ahead and describe this region. Instead of as a type 1 region, we're going to describe it as a type 2 region. And I'll do that in blue. So to describe it as a type 2 region in blue, I need to know what are the bounds on my x values as a function of y. I see my x's have a lower bound down here at x equals 0, and they can grow and grow and grow and grow until they hit the line x equals y. So in this case, the bounds on my x values are from x equals 0 until x equals y. And notice that in and of itself could trace out a whole bunch of places, but we only want our y values to go from down here to up here. So in this case, our y values are going to go from 0 to 1. This is a very, well, notice that I didn't exactly flip 1 to 1 exactly what's going on here, that my bounds on my x function are different than the bounds that we see here on our y function. So we really do have to draw the picture, describe the region, to be able to figure out how we interchange the bounds when we change our order of integration. But now that we've done this hard work drawing the picture, the rest of this ends up being pretty easy. So we just decided that we could change the order of integration by flipping from a type 1 region to a type 2 region. And it means that our new integral in this case, the outer bounds on our integral are going to be the constant bounds on the y. So y is going to go from 0 to 1. The inner bounds on the function are going to be the bounds on the x. So in this case, x is going to go from 0 to y. The function stays the same. The function in this case is just whatever's going up in the z plane. And z, it doesn't really matter what's going on. So nothing changes here. Sine of y squared dx, because x is now on the inside, dy. So let's integrate. The sine of y squared, we're actually just going to think of this as a constant because we're integrating with respect to x. So taking the outer integrals along just for the ride, I'm going to integrate with respect to x, and this is just a constant, so that becomes x times this constant, sine of y squared. And I'm going to evaluate it from x equals 0 to y. The outer integral is along for the ride. I'm going to plug this in as x goes from y to 0, and I see that I get y sine of y squared minus 0, because I would have to subtract out the lower bound, which is just 0. I need a little more space here, sorry. Should have written this down here. So y times the sine of y squared. And now we're down to a single variable integral. And this is something that's old school. So now I just need to integrate this. Unlike before, when we didn't have a term that could be a u sub, now we do. So now I'm going to do a u substitution where I'm going to let u be equal to y squared. And that means that du, in this case, is equal to 2y dy. And the fortunate thing is that I have a y dy. I don't have a 2y dy, so it means that when I solve, there are a number of different ways that you can think about doing this. I'm going to divide both sides by 2, and I know that 1/2 du is equal to y dy. So in this case, my y dy is going to become a 1/2 du. So 1/2 du is going to be equal to the sine of u. I'm going to integrate this with respect to u, and when I integrate this with respect to u, the sine of u is the negative cosine of u, and the 1/2 is just a coefficient. So going over here, I see that when I integrate this function with respect to u, I end up with the negative cosine of u times 1/2, evaluated from where y is equal to 0 to 1. So I need to go back and plug in my y's so that I can evaluate this. So u, remember, was equal to y squared, so I have the negative cosine of y squared. Maybe I'll take this and make it negative 1/2 cosine y squared, evaluated from y equals 0 to 1, becomes negative 1/2 cosine of y squared, which is just 1 squared, minus negative 1/2 cosine of 0. Cosine of 0 is 1. Cosine of 1 is some crazy random number that we don't really know what it is, so I'm just going to leave it like that. And we get our final answer. Negative 1/2 cosine of 1 plus cosine of 0 is 1. So this becomes plus 1/2. And this is our final solution. So recall in this technique when we interchanged the order of integration, so we interchanged which variables we integrated first. We had to look at our region and then change our region from the type 1 region it was into a type 2 region. And then we could integrate the way that we expected.